Okay, we're going to have a look at using the mass energy equation to solve this question here. So the first thing we need to do is to calculate, it says use the data in the table to calculate the mass on each side of the equation. So in the reactants, we've got one uranium nucleus and one neutron. So I've written the one uranium mass and the one neutron mass. Now when they're both multiplied by 10 to the power of negative 27, I find it easier not to put that number in my calculator. So I'm just going to write it here and then just add these two numbers together. And when I add those two together on my calculator, I get 391.8909. Okay. And then I'm going to do the same with the products, but I need to be very careful here because I've got one barium, one krypton, and two neutrons. So I need to add four things together. And when I put all of that into my calculator, I get 391.57088. And again, I haven't put the negative 10 to the power of negative 27 in my calculator because they've all multiplied by 10 to the power of negative 27. So I've just brought that down and just added those four numbers together to get that. Just have a check here, remembering that the mass of the products is always going to be less than the mass of the reactants because that mass is lost as energy. So to calculate the change in mass, it's the mass of the product here minus the mass of the reactants. And again, they're both multiplied by 10 to the power of negative 27. So I'm just going to do my 391.57088 minus 391.8909. And when I do that, I get negative 0.32002. And again, I'm going to bring down my 10 to the power of negative 27. I guess more correctly, we could do that and put that in brackets. Okay, so that's our change in mass, remembering that it's negative because there's a decrease in mass. Now I'm going to use that to calculate the energy. And that is change in mass times the speed of light squared. So I'm going to take this number. This time I can ignore the negative. 0.32002 times 10 to the power of negative 27 times 3 times 10 to the power of 8 squared. Okay, just be very careful in putting that into your calculator and you should get an answer of 2.88 times 10 to the power of negative 11 joules. So that's the amount of energy released when a neutron bombards a uranium nucleus. Okay, so those are the answers to parts 1, 2 and 3 of A. And now for part B, we are told that 1 kilogram of uranium contains 2.56 times 10 to the power of 24 atoms. And we're asked to calculate the energy released when 50 grams splits or goes through fission reaction. So we need to first of all calculate how many atoms there are in the 50 grams. Okay, so if we assume that 1 kilogram is 100%, then 50 grams is going to be 1/20th or 0.05. And we're going to work out that amount of atoms. Okay, so that's your 50 grams. And when we do that, we get 1.28 times 10 to the power of 23 atoms. Okay, if you're not sure about that, then please ask me. Okay, that's 50 grams or 1/20th of the whole kilogram. And then each uranium nucleus releases 2.88 times 10 to the minus 11 joules of energy. So if each nuclide releases that much energy and we have that many nuclides, then we multiply them all together to get the total energy. So it's 1.28 times 10 to the 23 nuclides, and each one gives out 2.88 times 10 to the minus 11 joules of energy. Okay, and when you multiply all those together carefully in your calculator, you should get 3.6864 times 10 to the 12 joules of energy. Okay, now that's probably to three significant figures, that'll be 3.69 times 10 to the 12 joules. But I think if you've got all that way and got the answer correct, we're not going to be too worried if you haven't given us the right number of significant figures. So that's the answer to that question. Please ask if there's anything else you'd like us to go over. Thanks.